So now let's go back to this negative feedback. Now instead of calling it simply A, I will call it AS, where AS is, if it is a first order system, okay. So it is a first order system, which means you have only one pole and your DC gain is A. So the same op amp which has a DC gain of A, it will have A, because S equal to 0 it will have A, but now your gain is a function of frequency. So it will look like this. So this is your omega p, this is your A, and if this is 0 dB, or I am not calling it dB, so if this gain is unity, so what is the frequency at unity gain? A into omega p, okay. And what is the slope of this? Minus 20 dB per decade. Where does this come from? Minus 20 dB per decade?
In dB we write it as minus 20 log of the gain.
So what is the magnitude? Yes. How do you write it?
20 log of.
No, how do you write? Forget about from this. A over square root of 1 plus omega over omega p square. Correct. So the assumption in the Bode plot is that omega over omega p is what? Much larger than 1. Correct. So what would happen? Your AS will become, magnitude of AS will become A times, what will be this? Omega p over omega. Correct. Now if you keep omega equal to 10 times of omega p, okay. So 10 times, when we say, we assume that this is 10 times obviously is much more than ratio of 10 omega or omega p, it will become 100, okay, and 100 is much larger than obviously 1, and that is the assumption we take. But if you look at omega, the frequency, pole frequency, where here we are assuming that your gain is A, but if you put omega equal to omega p, this will have a square root 2 factor, and that will, which means the gain will be dropped by 3 dB, and that is why we call it 3 dB frequency. In the Bode, ideally we show like this, but in the reality it is going to be like this, okay. You will have a, so this gain will be A over square root 2, okay. So if you want to be more precise, you always consider this square root 2 factor, but most of the time during analysis we do not do this, okay. And so if you do not consider this square root 2 factor, then you might see some difference in your actual result compared to what theoretically you have calculated, okay. So whenever you calculate the UGB and phase margin, all those, you might be off by 4-5 degrees always, if you do not consider this square root 2 factor, okay. So which means at every 10 times of the frequency, you will drop by minus 20 dB, okay. It is a linear, okay. So in the log linear you have a minus 20 dB, log 10 if you take, then it will become 20 dB. So that's why we say 20 dB per decade drop. Now if you have a 2 poles, then what will happen? Let's say same frequency 2 poles. So this omega over omega p will become a omega over omega p square, and in the logarithmic term square is nothing but multiplied by 2. So 20 into 2, that it will become minus 40 dB per decade. So you have to just keep, depending on number of poles, you have to keep just multiply by 20 dB multiplied by number of poles, you will get that. So now this is your open loop, and where is the pole here? Left hand side or right hand side?
Left hand.
So it's a left hand side, so intuitively you can say it's a stable system. Okay, but is this true that when I say that the left hand side pole of this AS, am I supposed to look the left hand side pole of AS or overall? Overall what? Loop gain or closed loop system, what?
Overall loop.
By looking at the loop gain, the pole of the loop gain, can you just say that it's stable or unstable?
You should look at the gain margin. Phase margin.
No, not phase margin. I am looking at the pole location, left hand or right hand. So when you say left hand, right hand, that is defined for your closed loop, not the open loop. And when you define the phase margin, gain margin, that is for the open loop system, your loop gain. So there are two differences here. So when you are analyzing by looking at the pole location, whether it's a left half plane or right half plane, you are actually looking at the closed loop system. Okay, and when you look at the analyze it in terms of phase margin, gain margin, then you basically do it for your loop gain A beta. So that's, and since analyzing a closed loop system is more complicated, that's why we always do this, analyze this A beta or loop gain, because it simplifies everything. And think about, you have a second order system, you put in the closed loop system, which means, so let's say beta equal to 1. If a beta equal to 1, then this becomes your loop gain, correct? Now in the closed loop, you have to substitute that AS here in both the cases, you have to expand this. So your equation will become little bit complicated here. Okay, but there is a relationship between, I mean, so when you define in the closed loop, you for the second order system, you remember damping factor zeta and all those. Okay, so there is a relationship between zeta and your phase margin. I will talk about that later. And by looking at the phase margin, you can intuitively say that your zeta factor is somewhere around that. Okay. So in the first order system, so how the step response will look like for first order system? If this is your V in, so what will be V out? How will it look like? Step response.
1 minus e power minus.
So one way, like you just A over 1 plus S, you know the transfer function of AS. Now substitute here A over 1 plus A beta, that will give you your closed loop transfer function, and from there you do the inverse Laplace and you will get exponential term. Okay. And this is your time constant tau. If you write in terms of RC, then it becomes RC or equal to 1 over omega p, which is your pole. Okay, closed loop pole, not the open loop pole. So let me say omega p dash. So the location of closed loop pole will change when you connect in the feedback. In the first order system, obviously it will become gain times of your, so that will be pushed at a times omega p, but in the second order system it becomes little bit more complicated. So first order system is always stable as long as your pole is in the left half plane. If you make it in the right half plane, then what will happen? This system will become 1 minus s over omega p. Okay. I mean, I am just saying that this will become, but where you have to look into the closed loop perspective. Okay. So when your closed loop pole becomes comes in the right half plane, then what will happen? This exponential term will become, if you look at the keep increasing actually. So step in the step response, so this is the step response. If you look at the impulse response, it will just exponentially decay out. Okay, it will start with 1 and then go to the 0. But in case of right half plane, it will be e to the power, instead of minus 80 it will be plus 80 and it will keep increasing. Okay. So you would have already studied in signals and systems or control theory. So now, so we know that single or first order system is always stable as long as pole in closed loop remains left half plane. Okay. So what could be the phase margin? What will the phase margin with? So anyway, let me go back to this Bode. This is one. So how do you draw the phase of this, your loop gain? So this is nothing but your loop gain. So where will it start from? 0? So negative feedback, huh? So 180 is already there, huh? 180 phase shift is already there even at a 0 frequency or DC. So you have to start with 180, you cannot start with 0. So in some case, some people start with minus 180 in order to show, because pole has a negative phase. So which means from, if you start from 180, you are going from 180 towards 0. If you start from minus 180, then you are going towards minus 360. Okay. So just show that your phase is moving in the same direction. Even in the simulator also you will find it might be showing from minus 180 instead of 180, but it doesn't make any difference as such. Okay. Ultimately 360 is same as 0 degree. So what will be the phase at pole frequency?
130.
So now your phase is what is the phase from one pole? Tan inverse what?
Tan inverse
Omega
omega by omega p.
by
Omega
omega p. So if you keep omega equal to omega p, tan inverse 1 is what? 45 degree. So which means at pole frequency you will drop by 45 degrees. So 180 minus 45 is 135. Now if you make omega equal to 10 times omega p, how much is that? Tan inverse 10. Should be around 85 degrees also.
around 96. Like angle is 84 degree. But
Okay.
tan is
So usually you say that, I mean, so if this is your, instead of starting from here, let me, so when you draw your Bode plot, you always take the logarithmic scale. So you make it omega p by 10 and this is 10 times omega p. Okay, and this is the point where your phase will start dropping. Tan inverse 0.1. Before that it will be roughly 0. And you say that this is 90 degree. This is actually approximate value, not the exact value. This 45 is very accurate, but when you say this starting point and ending point, this is approximate because you are showing on a linear curve, but it's not linear. So that's why I said when you consider this, even you don't consider the square root 2 in the gain and this 5 degree difference in case of this phase, then you will be slightly off. Okay, but this is a good way to get approximate value, and from there if you are just relying on the simulation, you can theoretically do with this, and from the simulation you can just how much tweaking you need to do and you can correct it. If you want to calculate more accurate value, you can just assume the exact values, square root 2 and this 5 degree difference you can take, and you will find the exact value also. That's not a problem, but in order to simplify the calculation we just assume this. So which means, and usually this tan 90 is infinity, so which means at infinite frequency the phase shift will become 90 degree, but usually we say that okay, by the time you have a 10 times of your frequency, go beyond 10 times beyond your omega p, then your phase will become 90 degree, and that's why we say the first order system has a phase margin of how much?
maximum phase margin
90 degree. Okay. So your phase will never go below, or sorry, your phase drop will never be more than 90 degree here. So when you measure the phase margin, you have to look at, so this is your unity gain point, your phase has saturated here. So what was the condition for instability? When would this system become unstable?
and the phase is
We just did saw that phase is 180 and gain,
and
minimum gain 1. By the way, there is something, what is that is called, the phase shift and gain 180. Barkhausian criteria. So if this is 0, this is the point where it will become unstable. So from that unstable point you have to see how much margin you have. Here margin is 90 degree. That's why we say phase margin is 90 degree. So in order to calculate the phase margin, or let me write, phase margin equal to 180 minus tan inverse omega over omega p. That becomes your phase margin, where omega is what? Omega UGB. Omega UGB is omega at loop gain unity. So at a unity gain, and that's why I call it unity gain frequency or unity gain bandwidth, UGF or UGB. So whatever contribution the phase you have from that pole at UGB, that will determine your phase margin.